Alright, welcome to the final homework solutions of the South Dakota School of Mines and Technology Thermodynamics 2 course. Homework number 8 is on equilibrium reaction thermo. Okay, so on the first problem, this is actually from the final exam. Okay, in these problems, essentially, I have a reaction and I have a problem. I'm given 3 choices on how to alleviate the problem at hand. Okay, so for this first one, I have CO plus water going to CO2 and hydrogen. Okay, the problem is, T is too high. Okay, so that's a problem. What are my possible solutions? I can either lower the pressure, I can remove water, or I can add CO. Okay. So those are my 3 choices. I'm trying to figure out which one is best, which one's indifferent, and so on and so forth. All right. So what do? First thing I do is I balance reaction. No matter what, I balance reaction. Okay? Or at least I check that it's balanced. Okay, I got 1 carbon, 1 carbon. 1 oxygen, 1 oxygen, 2 oxygens, 2 oxygens. 2 hydrogens, 2 hydrogens. All right, I am balanced. Now I write out the equilibrium constant and its relative formula. So I got K is equal to pi Fi over Fi naught to the new I. Okay. Now obviously that doesn't help me a ton, but it reminds me what I need to plug into here. I don't plug in moles, I don't plug in mole fractions, I don't skip ahead. I think about fugacities. Now, what's the fugacity of a vapor? Well, we're going to assume ideal gas, so it's just YIP. And because they're all gases, this simplifies down to N. If I call this one 1, this one 2, this one 3, this one 4, it simplifies down to N4 times N3 over N. When I clean the board, it's still a little wet, apparently. Okay, so let's try this again. N, let's try it over here. N4, N3 over N2, N1 times P to the new over N total to the new. Now, it's not perfect, but hopefully you can see that. Okay. Now, I'm going to wipe this because this is kind of wet. Okay. So, my first choice, so I'm saying the temperature is too high. So I'm trying to figure out a way to make T lower. Okay, so I can either lower the pressure, add water, or decrease, or remove water or add CO. Okay, now I'm looking at, okay, those are both products. Okay, and so really if I think about this, one is going to be good and one's going to be bad. I just have to figure out which one. Okay. So those are probably going to be opposite of each other. What about pressure? Well, I have to think about what's the nu of the reaction. The nu of the reaction is equal to the summation of the nu i's. Okay. Well, what's the nu of CO? Minus 1. H2O? Minus 1. Why is it minus? It's because it's a reactant. Okay, so when I add them all up, my nu of my reaction is actually 0. As a result, these are 1. Okay, it's P, pressure to the nu, when nu 0 is 1. Okay. So, I'm affecting N4, N3, or pressure to affect K, which is going to affect T. But I've already just said that P has no impact. So when I come to case 1, in terms of lowering the P, there's no impact. Now the problem also states why. I don't need 2 paragraphs of why. All I need to say is, well, nu is equal to 0, so P has no impact. That's all I need. I don't need anything more. Okay. All right, let's move on to water. And again, whatever water is going to be the opposite of CO. So most likely, this is a 2. Now, it could be a 1, it could be a 3, if both of these were bad. But I can look at this and know that one's going to be good and one's going to be bad. I'm just trying to figure out which it's going to be. Because, dehydrating water is not hard. I can add some sort of, there's a lot of, dehydrating agents to remove water from the air. Okay, so that's not crazy. Okay, adding more CO, that's not crazy either. So those are both viable options in terms of how I design this reactor. And that's what this really gets down to. It's not that I'm all of a sudden changing the pressure, all of a sudden adding an inert. I'm designing the reactor. I'm designing the reactor conditions. And so, do I place a dehydrator before it reaches the reactor or leave it be? Do I recycle the CO so that there's more CO in it? Or whatever. Okay. Again, to figure out a way to make it so that my temperature's not too high. Okay, so I said I would affect K. Okay, and so what I need K to be a value. So it's already a value. I need to either go up or down based on what T I want it to be. So I want T to go down. What does K need to do? It depends. It depends, is it exothermic or endothermic? How do I determine that? I obviously get heat of reaction. So let's see if I can write this one down. So I've got there we go, delta H naught of reaction is equal to summation of nu I delta H naught for component I of formation. Okay. Now on the final, I would expect you to just kind of eyeball it. Okay. It should be close, but we're going to explicitly calculate it. Okay. So let's do that. Okay. So I got CO, carbon monoxide. Okay. So that is minus 110.53 times minus 1 plus minus 1 times whatever it is for water as a vapor, which is minus 241.82, plus, that was CO2, plus 1 times negative 393.51, plus 1 times hydrogen, which is just 0. Okay. And so really I have all these and I just need to add them up. Eyeballing it, I got about 503 here, 504. So, well, no, I don't because there's the minus 1. Okay. So really I have 283. So I have minus 283 plus 241. So I am negative. So this is less than 0. Okay. By how much? It doesn't matter by how much. I don't need to know about how much. I just need to know that it's negative. And it being negative says what? It says that this is exothermic. Okay, so it's exothermic. It gives off heat. Okay. And so, now, if I wanted to improve extended reaction, this is how I want to think about this. Think about it as, okay, I want to extend, I know extended reaction is constant in this case, but that's how I want to start thinking about this. So it's extended reaction, what do I want to do with an exothermic reaction? I want to cool it down. there's a jerk burning a fire in the room. I want to turn down the thermostat so it doesn't get too hot in here. Okay, so I turn down the temperature. Because if I turn down the temperature, my K will go up, making my products go up. All right, that's how I normally think about it. Now I reverse that thought. I want temperature to go down. So what do I want K to do? Well, what will K do rather? Okay, so temperature goes down, K goes up again. I mean, it's the same thing. Okay, K goes up, so I need to figure out, so that's my goal. I want K to be big. Big as possible, because the bigger I get, the cooler I can have it. All right. Okay, so how do I do that? Now this is where I get into the math of going down here. All right, well, I add water, or sorry, I remove water. So I'm lowering N3 directly. I have no NT to affect, so really I'm affecting N3. And everything else is dependent upon squiggly. Okay. Because I mean, if I think about this, and if I did my table, and I don't need to do a table, but if I did my table, how this would look would be like, oh, sorry, I'm lowering N1. I mean, sorry, N2, not 3. So how this is looking, you know, is I got a squiggly times a squiggly over a 1 minus squiggly, or rather a 2 minus squiggly times a 2 minus squiggly. And okay, now I'm all of a sudden making this 2 a 1. What happens? I mean, everything else is the same except, you know, because I've designated squiggly as 0.95. You know, this 2 doesn't change here. You know, I've just made this a 1. Okay. So how does that affect the math? All right. Well, I've lowered the bottom. And so what does a division by a lower number mean? So if I use real numbers, like something simple, I mean, I could use 0.95s and 2s and stuff, but I'd rather just think about it as like, okay, I've got 2 times 2 over 2 times 2 versus 2 times 2 over 2 times 1. Okay, so this one is 4 divided by 4, which is 1. Okay, this one is 4 divided by 2, which is 2. Okay, so did it go up or did it go down? It went up, which means K had to go up, which means, because this is exothermic, T had to go down. And then I ask myself, is that a good thing? Well, I look at the problem statement. The problem statement says my T is too high, I want a lower temperature. So that's a good thing. Okay, the reason why? Because this is an exothermic reaction, and a lower amount of reactants will result in a higher K. Okay, so that train of thought, lower amount of reactants, because the conversion is the same, results in a higher K, and a higher K results in a lower required temperature, because it's exothermic. All right, and I'm going to get the exact opposite when it comes to CO, but just to show you, okay, again, I have like 2 times 2 over 2 times 2, and I'm going to 2 times 2 over 3 times 2. All right, well, I got now 4 divided by 6, which is about, you know, so I go from 1 to 2/3. That obviously went down. K went down. That means in an exothermic reaction, temperature has to go up to maintain the same conversion. Oh, well, temperature going up is a bad thing. So, I mean, that's a bad thing. So that's definitely a 3, because this one is indifferent. Okay, so in the rankings here is 2, 1, 3. And I just keep going through this in this manner. I'm going to split this video up into 3 parts.